Hi, and we're going to have a quick little look at how to do this practice quiz that you've been given. So this unit structures and how structure will affect properties. So in this particular quiz, you're going to be expected to do a few things. I have them listed out in question 1. It says, for the following questions, you will draw the Lewis structure of a compound, determine the electron domain geometry and molecular domain geometry, that is using VSEPR, or valence shell electron pair repulsion theory. You're going to determine the polarity of various bonds. You will determine the polarity of a whole molecule where appropriate. And finally, you will determine the intermolecular forces present in the molecule. I have picked 4 molecules in this particular practice, just because there are 4 polar ones in this one or 4 non-polar ones doesn't mean that that is what you would see on the quiz. Any of them would be fair game. So the first challenge for 2 points, you're going to be asked to determine the Lewis structure of these molecules. So let's start with question A. We have the nitrite ion, or NO2-1. First thing to do in a Lewis structure is to write the number of valence electrons. So nitrogen is in group 15, so it has 5 valence electrons. Oxygen is in group 16, so it has 6. I have 2 of them, so 6 plus 6 is equal to 12. And finally, I have a charge. So since it's a negative charge, that means that there is an extra electron, so I'm going to add 1 more. So 5 plus 12 is 17, plus 1 is 18 electrons. So we have 18 electrons to deal with, and normally the first element that is written, or the more electropositive one, will go in the center. And remember that it's electropositive, so the one that is less electronegative would go in the center. So we're going to put those two, the more electropositive one in the center, the 2 electronegative ones outside. Also, usually if you have 1 of a particular atom, that will also be your central atom, and generally we write the central atom first in the equation. So we're going to first just write the bonds. We're going to give it a quick little try. We're going to put 2 bonds, and we're going to keep track because that's what Lewis structures are. They are just electron accounting. So each bond counts as 2, so 2, 4, I just spent 4. That gives me 14 electrons remaining. I'm going to fill my octets, 2, 4, 6, 8, 10, 12. I just spent 12 filling the satellite ones, the oxygens. And I have 2 left, and I just spent those. So we're quickly going to have a quick check at this structure. In the left-hand side and the right-hand side one, their octets are satisfied. However, the central atom only has 2, 4, 6 electrons. That's not good. So we have to try something else. This was not the correct structure. So the first thing we're going to do is we're just going to make a double bond. So basically we're going to take one of those pairs and we're going to make a double bond. And I'm going to rewrite this all out. You can take us back to the start. So we start out with the 3 of them. We connect everything up, but this time we're going to add 2 bonds on this side and 1 on the other. It would be completely irrelevant as to which side that goes. So I have 18 electrons to start with. I just spent 2, 4, 6. Means I have 12 electrons left now. We're going to fill our octets. So 2, 4, 6, 8, 10. Meaning I have 2 left. The 2 left can go on the central atom, meaning I've spent them all. So again, this one was not good. Let's check our octets. 2, 4, 6, 8. That's okay. 2, 4, 6, 8. That's okay. 2, 4, 6, 8. That is okay. This is very likely the correct structure. I'm going to put it in square parentheses or brackets, and we're going to give it its charge. A couple of things. We know that the octet and the central atom cannot be broken, simply because it does have, it can't exceed 8 because it is quite high in the periodic table. It's only in period 2. And we were given an even number of electrons as well, so we know that we're not going to end up with a single electron on the central atom like you might with just nitrogen dioxide or something like that, if you were to draw that molecule out. So this is the correct structure. We're going to do the electron domain geometry. First things first, we have to count the number of electron domains. I have 1, 2, remembering double and triple bonds, I'll only count for 1. So 1, 2, and then I have the lone pair, which is 3. 3 electron domains means that the electron domain geometry, using our chart, or hopefully from memory at this point, would be something called trigonal planar. I have 2 bonding domains and 1 non-bonding domain. When we look that up in the structure, we will find that this molecule is in fact bent. So that was question 2. Question 3, it says determine the polarity of the bonds. So the difference in electronegativity for a nitrogen-oxygen bond is equal to, pull this out if we need to, nitrogen is 3 and oxygen is 3.5. So the difference between those is 0.5, which we have decided that is not polar in this situation, or very, very weakly polar. And that difference can be relevant here. If you would say that 0.5 is polar, then that will change your answer for part 4. If you say that 0.5 is still considered in the nonpolar covalent range, the chances that you would have to say that this molecule is not polar. So we know this molecule is bent, and just to try and consider this, we have this molecule. We know that if this bond is even slightly polar, again 0.5 is the cutoff, we know that we're going to have a structure like this, where we're going to have 2 polar poles away from the nitrogen with a lone pair up on top. There's one thing that we're not considering at all, and that is the fact that this molecule is actually an ion. So somewhere in this molecule there is a negative charge, and it's generally spread throughout the whole molecule. In other words, there's an extra electron floating around. So even though we can start talking about how close this is to a polar bond, in this particular example, because the molecule itself is an ion, I'm going to write that this is not applicable. It is an ion. So this means that the whole molecule is negatively charged. And where that negative charge is probably concentrated on the oxygens and making the nitrogen slightly positive, but there's so much negativity on these oxygens because of that extra electron that we can't really even talk about polar molecules. We're going to talk about ion. But again, very likely that if we were to draw an electron cloud, there would be a lot more on those oxygens than the nitrogen. Finally, it says determine the intermolecular forces present in the molecule. So we basically can start them all by just writing dispersion. There is dispersion in every single molecule. In this particular case, it will not be the most strong. We are going to have ionic forces, which is technically an intramolecular force, because if it comes closer to any cation, it will of course associate with those. And then we can also have ion dipole, which is very likely the number one answer that we'd be looking for here, and that's only if a dipole is present. So that's what we're going to do for A. So we have a structure, we have the geometry, we have difference in electronegativity, but we've decided that it is not relevant because the molecule itself is negatively charged. This would also be true if the molecule was positive. And finally, we looked at the intermolecular forces that could be present. So let's go over to B. we have a bunch of molecules from group 16, so they all have 6 electrons. So sulfur has 6, and each oxygen has 6. So this whole molecule has 24 electrons. So let's write it with sulfur in the middle. Let's put our oxygens around. So let's start counting. Let's put bonds in place. 2, 4, 6. Now, we've been doing something within our class where we simply did the number of electrons that are needed, and we looked at the number of electrons that we want. So every atom in here wants 8. So we know that we have 4 atoms times 8 is going to be 32 electrons. So we're going to create an environment of 32 electrons. We only have 24 electrons to do that, and each bond is going to take 2. We can do this simple calculation. How many electrons are wanted, how many electrons we have, and divide 2 per bond. 32 take away 24 is equal to 8. Divide by 2 is equal to 4. So that gives us a pretty good idea of how many bonds that we want, which is 4. So I'm going to add an extra 1. If you want to take the approach to go through all the counting and then have to add 1 and redraw it like we did in letter A, that also would work here. So 2, 4, 6, 8. I just spent 8 electrons in bonding, leaving me with 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. Spent them all. That is a pretty good molecule. We also know that this, just like A, is also a resonance structure. That double bond could have been in any particular place. There would be 3 resonance structures that would be possible for the 3 different locations we could put the double bond. So we're going to do the electron domain geometry and molecular domain geometry for this using VSEPR. So we have 1, 2, 3 electron domains. We know that that is trigonal planar. Anytime that the electron domain geometry consists of nothing but bonding pairs or bonding domains, we know that the molecular domain is the same. We go down and we're going to calculate the polarity of this, but we have 3 groups that are identical, so we know that the overall molecule is probably not polar anyway. So we look at sulfur. Sulfur is 2.5 and oxygen is 3.5. What we have done throughout our course is simply highlight bonds that are polar. So we'll continue that process here because 1.0 is definitely in the polar covalent range. Now we look at the shape. This is trigonal planar with 3 of the same substituents. There is a resonance bond here, but it's probably not going to have very much of effect because it's going to essentially cancel it out, and the electrons will be, all 3 of these bonds will essentially be equal. So this molecule is actually nonpolar. And since it's nonpolar, the only forces that we expect are dispersion forces. Let's go down and look at number 2. Number 2 says, which of the above compounds in question 1 would be better at conducting electricity? Explain. So, pretty straightforward question. It's testing knowledge that you understand the difference between molecular and ionic compounds, or molecular and compounds and ions. In a solution of nitrite, assuming it would have to be dissolved in water in this case, what we hope to see is how can charge be passed along. In molecular compounds, the conductivity is very low or poor. So B is not going to be a great choice because it is a nonpolar molecule. However, this molecule is an ion, and ions are much better at conducting electricity. So the answer would be A. And the explanation Ions can conduct charge. It can create a flow of charge. So let's go to the next page. We're going to look at question 3. It's going to look pretty familiar for what we just did. It says, for the following questions you will, and then we're going to do the exact same things. Now, what I want to draw attention to here is a very particular fact. So we have them side by side. We have A and B for part 3 as well. So we have dichloromethane, which simply means we have a carbon backbone and 2 chlorine atoms attached, and the rest is hydrogen. This is dibromomethane, so we have a carbon backbone, 2 bromine attached, and the rest are hydrogen. So we can go through and do this process. We know that we have carbon in group 14, that's 4 valence. Hydrogen each brings 1, so that's 2. And chlorine each brings 7, which is 14. So 4 plus 2 plus 14 is equal to 20 electrons. I'm almost going to do these drawings concurrently, just simply because that chlorine and bromine are in the same group. So their number of valence electrons will be the same. So I'm still going to end up with 4 plus 2 plus 14, which also has 20 electrons. Bromine is just a bigger molecule, so it has more electrons involved in what it's doing, but the valence electrons are the same. So we start with our carbon in the center. Let's bond it to our hydrogens. Let's put our chlorines in there. And we are supposed to be electron accountants, so let's make sure that we are still accounting. We have 20 electrons. We just spent 8, leaving me with 12. 2, 4, 6, 8, 10, 12. Just spent them all. This molecule here is going to look exactly the same, with the only exception being instead of Cl's, we're going to have Brs. And you can go through and check the electron counts to make sure that that is true, but I think you should just trust me on this. I can make this explanation a little shorter just by making that assumption. So again, molecules very, very similar. We're going to have a lot of similarities here, so hopefully we're going to have to emphasize the differences. The electron domain geometry for this molecule has 1, 2, 3, 4 electron domains. That's tetrahedral. This has 1, 2, 3, 4 electron domains, also tetrahedral. We know that anytime there are a number of electron domains, in this case 4, and they are all bonding domains, that the electron domain geometry and molecular domain geometry are the same. So I'm going to write the fellows in. A lot of similarities between these two. Again, your molecular domain geometry is the same as your electron domain geometry if all of the electron domains are actually bonding domains. So for 3, we're going to have a couple differences here. We're going to calculate difference in electronegativity. So we're going to do it between carbon and hydrogen. Pull out my little chart here. Carbon is 2.5, hydrogen is 2.1. Although hydrogen is more electropositive, it never can be in the center because it can only take 2 electrons. The difference is 0.4. Difference in electronegativity between carbon and chlorine in this case is going to be equal to 3.0 take away 2.5 equals 0.5. So again, we're at that cutoff range, and we get into a little bit of a gray area as to whether that or not that's a polar bond. It really depends on who is talking and who you ask. Generally with 2 0.5s, we're going to move the molecule into a very, very weak polar, but essentially this molecule is going to behave a lot like nonpolar compounds. The change in electronegativity for this one is going to be 0.4, and that's the carbon-hydrogen bond. And the change in electronegativity for the carbon-bromine bond is going to be equal to 2.8 take away 2.5 is 0.3. So this molecule is very, very nonpolar. This one is also nonpolar. We know there's going to be a slightly heavier electron concentration on the chlorines. Whether you want to give the molecule a slight negative and a slight positive charge on the chlorine would kind of be based on how you've been taught and what textbooks you're using. Again, remember there's a continuum of bonding that are involved here. Both of these chlorines will be pulling slightly, but the balancing of the hydrogens pulling back, the difference is just too close in a tetrahedral to really give it any difference. This one, both molecules are clearly, both bond types are clearly nonpolar, so we don't have to worry. So I'm going to actually go out and say that these are nonpolar, both of them. If they are both nonpolar, the only difference are your dispersion forces. Well, I'm just going to take a little bit of an initiative here, and I want to actually look at the molecular weight of both of these. And this is going to be one of the biggest differences, is the size of chlorine compared to bromine. So dichloromethane has a molecular weight of 84.9 grams per mole, thereabouts anyway. And bromines are 79.9 grams per mole times 2 plus 12 plus 2 is 173.8 grams per mole. So pretty big difference between the two of them. Basically a factor of 2 in their molecular weight. So it says these molecules are very similar. Dichloromethane boils at 39.6 degrees. So that's this one, and the other one boils at 96.95 degrees Celsius. So there's a difference in properties, and that is the point of this unit. This is what we're trying to get you to do. The only difference between these two molecules are the chlorine and the bromines, and ultimately the molecular weight. So the molecular weight must be what is causing this difference. We know that we have dispersion forces, so we're going to think back to what we did in class about what dispersion forces do. There are two things that affect dispersion forces. One is molecular shape, so long chains have more dispersion forces than grouped or spherical molecules, regardless of the weight. And the more important of the two is the size of the molecule. More electrons means a higher chance of those electrons becoming polarized or being distorted. So dispersion forces are stronger in bigger molecules. So CH2PR2 is larger, giving it more and stronger intermolecular forces. So that's basically what we are trying to get you to show in this question, is that you understand that the size of a molecule affects the dispersion forces. And in molecules that only have dispersion forces, like these two, again, just dispersion involved, then the size has got to be the biggest factor, since they have exactly the same shape. Now, for question 5, it says, based on the information for question 4, predict the boiling point for CH2I2, so diodomethane. Well, let's look at where we are on the periodic table specifically. So we're in group 17. We did dichloromethane is at 39 degrees. this one is at 96 degrees. So that's that's the difference between 60. Let's assume that that trend continues. So dichloromethane, then we end up at 40 degrees essentially, 96 to 100 degrees-ish. So this one's going to probably go up by another 60. So that's my thought here on this. But let's assume that the pattern stays linear. We did this in class doing boiling points for another compound, so let's assume that the linear trend will continue. So 96.95, let's call it 97 plus 60, be 157 is my prediction. And if we go online and we look that up, you'll find that it's actually 180 degrees Celsius. It is quite a bit larger than we predict, but the issue for iodine is it's starting to get quite a bit bigger. The molecules are being attracted a little bit differently, so we do expect a little bit of variance in those molecules